Welcome back, and we'll continue with question number 3 from the thinking question set. And remember, we are reviewing for a unit test number 3, which is about derivatives. Here we have to determine the equation of the lines that are tangent to y equals x squared plus 3x plus 1 and pass through the origin. So the information given here is that we have the equation of some function. So this is a quadratic function in the form x squared plus 3x plus 1. And what we are trying to do is draw a tangent line on the graph of this function. And the tangent lines must pass through the origin. Now, the origin will have the coordinate 0, 0. And remember that 0, 0 is not a point on the parabola. So we are not in a situation where we have some parabola and we're asked to draw the tangent line or find the equation of it. But we have a point outside of the parabola and trying to draw tangent lines to it. So to have a better idea of what is happening here, what we are going to do is take a look at the graph of x squared plus 3x plus 1, which I prepared in advance, which you can do as well at home when we are practicing by using Desmos simply, so for speed, obviously. So this is a graph of x squared plus 3x plus 1, and this is the origin, 0, 0. And from the origin, it seems that we are drawing tangent lines. So one is passing through this particular point here. Let me try my best here to touch that. Yeah, that looks like a tangent line. And another tangent line will be right here. So let me just change the color of it so that we can see and tell exactly what's going on. There we go. So as you can see, from a point outside the graph of a parabola, we can draw two tangents. So what we are trying to do is find the equations of each tangent, which means that we will have to find an equation in the form y equals mx plus b, and we will have to find another equation in the form y equals mx plus b. I'm going to try to make this a little darker because it doesn't look very good here. So y equals mx plus b. So here we go again. Now remember what things these two tangent lines will have in common. So as you can see, 0, 0 is a point that passes through the origin of the Cartesian plane, or should we say on the y-axis. So it seems that the y-axis in here will host the y-intercept of both tangent lines. So therefore, we're going to say that we're practically looking for equations of two different tangent lines, but what they have in common is their y-intercept. So the y-intercept will be equal to 0. And obviously, these two tangent lines will have different slopes. And our task now would be to find the slope of each tangent line. So remember that whenever we say slope, we mean the derivative of a function, so which means that the slope of the tangent at any point on the graph of this parabola will be given by the derivative of function y, which means that with y being x squared plus 3x plus 1, we'll have the derivative 2x plus 3. So what does this equation or what does this expression do for us? So 2x plus 3 can provide us with the value of the slope at any possible point on the parabola. So if we want to know what the slope of the tangent is at x equals, for example, negative 3, you substitute negative 3 in, and it will give you the exact value of the slope here. If x equals negative 4, then you substitute negative 4 for x, it will give you the slope of the tangent here. If x equals, for example, 0, then you substitute x by 0, and it will give you the exact value of the slope. Now, I hope that these examples now can help you understand that in our case, we're not looking for the slope of the tangent at any point. So we are looking for the slope of the tangent drawn at these two specific points whose values we still are unsure of what they are. So we don't know these values. But we do know that once we have the values of x where the tangent is touching the graph, then we can easily substitute the value of x in here and then find the slope of the tangent. So how do we find the coordinates of the point of tangency? So to find the coordinates of the point at the point of tangency for these two very specific points, we definitely can use the slope of the tangent at any point, because if it works for any point of the parabola, it will work for these two as well. Now, because these two tangent lines are drawn from a specific point on the Cartesian plane, it means that the slope of the tangent must also be equal to a rise over run of the line that is created from connecting the origin with a point of tangency. So remember that the coordinates of any point on the parabola can be described by using the equation of the parabola. So at any point with coordinate x, the y-coordinate will be x squared plus 3x plus 1. So I want you to try to imagine that we are drawing a straight line, which in this case is tangent to the graph of this quadratic function. So we are drawing a straight line that connects the point with coordinates 0, 0 and the point with coordinates x and x squared plus 3x plus 1. So to find the slope of the tangent that connects these 2 points, then we're going to say that we simply have to use the formula delta y over delta x. Now, delta y, remember this is going to be the y at the point of tangency, and this is the y at the origin. Now, I'm going to call this y1 and this one y2, and similarly we'll call this one here x1 and this one x2. So by using the formula x2 minus x1, y2 minus y1, we can just figure out the ratio delta y over delta x. So we'll have x squared plus 3x plus 1 minus y1, which is 0, divided by x2, which is simply x, minus x1, which is 0. So the slope of the tangent can also be described as the ratio x squared plus 3x plus 1 over x. So remember that this would be the slope of the tangent at any point on the parabola, including the 2 points we're interested in. And this would be the slope of the tangent drawn from 0, 0 onto any point on the parabola, because any point on the parabola can be described by these 2 coordinates. So since these 2 expressions represent the slope of the tangent at any point on the parabola, what we're going to do is equate them. So we'll say that 2x plus 3 equals x squared plus 3x plus 1 divided by x. As you can see here, we have created an equation. It looks like a rational equation, which we are about to solve. And the way we do it is, obviously there are many different ways of solving these equations. I'm simply going to show the cross multiplication method. So I'll turn the left side into a fraction or rational expression, and we'll cross multiply. So that will give 2x plus 3 multiplied by x equals x squared plus 3x plus 1. And from here on, we simply continue solving the equation. It looks like a quadratic equation we've created here. So we have 2x squared plus 3x. And in the meantime, since we notice that we have created a quadratic equation here, we'll take all the terms to the left side. So either side again works. So equals 0. So 2x squared and negative x squared are like terms, so that will give x squared. Now as you notice, 3x and negative 3x will simplify to 0. So we have x squared minus 1 equals 0. So you can solve this by factoring. You can solve this by simply taking the constant to the other side. We have x squared equals 1, which makes x equal to plus or minus 1. So what that means is that we have 2 different points of tangency, and we're not surprised about that because we do know that we were able to draw 2 different tangent lines. And it seems that the points of tangency are exactly at x equals 1 and x equals negative 1. So knowing the coordinates at the point of tangency will help us find the equation and the slope of the tangent. So we'll get started with the slope of the tangent first. So I will be grabbing again this equation here and this equation here, so both of them. Now remember that we've already figured out the y-intercept. And we know that the equation of the first tangent will be y equals mx, and so will the equation of the second tangent line, y equals mx, but their slopes will be different. So in order to determine the slope of the tangent, then we will have to use the x-coordinate at the point of tangency. And for the pink tangent here, we can tell that the x-coordinate is equal to 1. So with the x-coordinate equal to 1, we can find out the slope. So we say at x equals 1, the slope equals f prime at 1. And remember that the derivative, which gives us the slope, is 2x plus 3. So that will make it 2 times 1 plus 3. So again, I'm just going to write this down. So f prime of x equals 2x plus 3, which will make the slope 2 times 1 plus 3, and that would be equal to 5. So therefore, we're going to say that the equation of the first tangent, the one drawn at x equals 1, would be y equals 5x. And in a similar way, we find the equation of the second line. Now remember that here we drew the tangent line at x equals -1, which means that the slope would be equal to the derivative at -1. Remember that f prime x is 2x plus 3, which means that f prime at -1 would be equal to 2 times -1 plus 3, or 1. So therefore, the equation of the second tangent will be y equals 1x, or simply y equals x. And that would be the second tangent line. And if you look at the graph of this parabola and the tangent lines, you can tell that the blue parabola does seem to have a slope of 1. And the pink tangent here, the blue tangent has a slope of 1, and the pink tangent seems to have a steeper slope, so a slope of 5. So you rise 5 units and you run 1 in order to hit the point of tangency, which is right there. And I hope this made sense and it helped you understand how to approach problems of this nature, of similar nature. And again, thank you for learning with me. Thanks, and bye for now.